Hello, good morning. Today I'm gonna explain about lab 5 and lab 6. Lab 5 is about conservation of linear momentum. Lab 6 is Hooke's law. Yeah. So I'm gonna first explain about lab 5. Okay, let me share the lab manual here. This is a lab manual. And then in this lab manual, you can read here the title of the experiment is conservation of linear momentum. Objectives is to study the types of collision in one dimension between two balls by using base simulations. So, okay, so this is we're gonna theoretical background is like this. We have to think there are two kind of collisions. One is elastic collision, another is inelastic collisions. Inelastic collisions. Yeah. What difference between elastic collisions and inelastic collisions? This is you can see here. So let me share PowerPoint here. Okay. Lab 5. Lab 5 is conservation of linear momentum. Here, important things we have to think about collisions. Two kind of collisions. There are elastic collisions, yeah, and inelastic collision. And we can think here if I draw a table like this, and elastic collision is we think is momentum conservation. First, we can think of kinetic energy conservation. For elastic collision is conserved, but in elastic collision not conserved. And what about momentum conservation? Linear momentum, precisely momentum conservation. Momentum conservation. Momentum conservation are satisfied in both cases. We have to check this statement through this experiment. What is momentum conservation? Momentum conservation means you think momentum conservation. Conservation is if I have two balls there and this ball, and we think initial, if I think this is first ball, this ball 2, then initial momentum of ball 1 plus initial momentum of ball 2, that is total momentum, is equal to final momentum ball 1, final momentum of ball 2. It's like this. This kind of statement we have to check. Also, we have to check energy conservation too here. Then now come back to the lab manual here. Let me read it. Yes, also experiment too is we have to think of elastic collision case, and both the balls have same masses, equal mass case. And click on, we have to see this base simulator, and maybe I have to use this one. Okay, here's we come back to, and what is this one? Let's oh, this is lab 5. Then here we have to see first to click the, then second one is select elasticity 100%. It means elastic collision, perfect elastic by dragging blue triangle to the right side. We can come back to the blue triangle has elasticity just 100% there as not triangle. In this case, this level, yeah, 100%. And what else do we need to do? Select M1 and M2 2 kilogram. M1 and M2 2 kilogram. We have to measure 2 kilogram, 2 kilogram. Enter. This is 2 kilogram. And not this, just 2 kilogram. Enter. And then the next one is next things. What else do we need to? Number 4, number 5 is position 1 meter, position 1 negative 1 meter, position of ball 2 is 0 meter. Back to 1 is negative 1 is you cannot see that position data. In that case, you have to click this option, more data. Then position of particle 1 is negative 1, position of particle 2 is 0. Then what else? Select initial velocity of ball 1 is 2 meters per second. Ball velocity of ball 2 is 0 meters per second. You can see it. 2 meters per second. 2, yeah, this is 2. Ball 1's velocity is 2. Ball 1's velocity is 0, right? And then it means, you know, this first ball is only moving, then second ball is originally at rest. Then, yeah, then we have to collect the data. Yeah. So what happens? We have to play this one, and you have to click this triangle play button. You can see here. So we can see is momentum. The final velocity is first ball is 0. The final velocity of the second ball is 2. Let's switch it. So we can build the data. Data table. The next day here, so we can see first one is momentum become 0, 2. Then you know here is the momentum of initial M1 V1 is equal to, because M1 is M2 is equal to 2 kilogram. 2 kilogram. This is a table 1. This is a table 1. 2 kilogram. Then we have to see here is the momentum of this is 2 times 2 is 4. Then final momentum is 2 times 2 is also 4. Right, the mass of the ball is 2 kilograms, right? As I said, this is 2 kilograms. Right. Then we can see here is total kinetic energy. Kinetic energy is how to get kinetic energy. You know, 1/2 times m is 2 times v1 I is 2 squared equals, this is what is that? This is 4. This is the ratio of that 4 is equal to 1. Then final momentum is also similar to Kf is equal to 1/2 times 2 squared is equal to 4 and 4. Then and Kf over Ki equal to 4/4 is equal to 1. All right, we set 2.5 meter per second. 2.5 meter per second. No. This is we have to come back original case 2.5. Then we have to replay after setting adjusting velocity of initial velocity of the ball 1. And what happened? You can see here is velocity of ball 1, final velocity of ball 1 can be 0, and final velocity of the ball 2 is 2.5. We can see that. And we can write is 2.5 case 0, 2.5. Then similarly, if we find pi equal to 2 times 2.5 equal to 5. 5. This is also 5. Then ratio can be 1. Then what about momentum? Is energy, kinetic energy 1/2 times 2 times 2.5 squared. Then this can be 6.25. 6.25. Kf is also 1/2 times 2 times 2.5 squared. That can be also 6.25. 6.251. You can see here, check it. It means Kf, Ki, it means this is Kf and Ki is same. Means initial total kinetic energy and final total kinetic energy is conserved. It means you can conclude, oh yeah, momentum, before and after collisions are conserved. Conserved means it doesn't change it. And kinetic energy before and after collisions are conserved. This statement we proved through this table. Then what else? The next table is table 2. In this case, we have to think. I can come back to table. This table 1 and table 2 is elastic collision, but of different mass cases. Use the same link. We can then keep elastic. This is 100% blue, something not triangular. Then 3 kilogram, 2 kilogram. This is changing. Come back to our simulation. 3 kilogram, and 2 kilogram. 3 kilogram, 2 kilogram. 2 kilogram. This 3 and 2 kilogram, just same. Then what else? Then position is -1 and 0, same. But position is -1 and 0. And what else? What then? That's all. The initial velocity is v1, I is 1 meter, another is 0.5. Both are moving. 1 and 0.5. 1, 0.5, 0.25. Then we have to play. Yeah, let's play. Let's start. You can see here is yeah. It's a velocity change 0.6, 1.1. We can go back to our table. And this is M1 is, as we see, 3 kilogram, M2 is 2 kilogram. 2 kilogram. Okay, so and then after collision it was 1 and 0.5. Then 0.6 and 1.1. 0.6, 1.1. Then we can find the initial momentum. Initial momentum is M1 is 3 times V1I is equal to 0.6 plus mass is 2, M2 is 2 times V. Oh no, this is 1. Sorry, this is 1. Initial case, initial 3 times 1, then 2 times 0.5, 0.5. That is 3 plus 1 equal to 4 kilogram meter per second. What about final? This is 4. Final case M1 is 3 times final velocity 0.6 plus 2 times final velocity 1.1. That we add them 1.1 plus 2.2 equal to 4 kilogram meter per second. Yeah, of course, this also momentum is conserved. Like PF over PI is equal to 1. we can see 1.5.75 case. We can change the initial velocity 1.5.75 case. And the velocity. And we have to reset. Initial position is 0 and -1, 0, and 1.5, 1.5, 0.275. Then what happened? We're gonna see here. We're gonna play. After collision, its velocity is 0.9, 1.65. 0.9, 1.65. 0.9, 0.65. Right? Is it right? 0.9, 1.65. 1.65. 1.65. Right. Then we can calculate PI is equal to 3 times 0.9 plus 2 times 1. This 1.5, 1.5, 2 times 0.75. 5 course this is then 4.5 plus 1.5. That can be 6 kilogram meter per second. Kilogram meter per second. Then the PF is equal to 3 times 1.5 instead 0.9 times 2 times 1.65. That this can be what else? And 2.7 plus 3.3. That can be 6. Then this also 6. The ratio. What about kinetic energy? This we did this experiment. We can calculate this 1.1. And initial kinetic energy. Initial kinetic energy is 0.25. This means 1/2. 1 times 0.6 square plus 1/2 times this message 3, 2 times 1 square plus 0.5 square. And this is 1.5 plus 0.25. This cancel. 1.75 joule. Then overall Kf is 102 times 3 times velocity 0.6 squared plus 102 times 2 times 1.1 squared. Then this if we multiply, this is 0.36.18 times 3 is 0.54. Also, this is the 1.21. This can be 1.75. 1.75. 1.75. Both of them, but then ratio must be 1. And then what about here is 1? We can use this data. Then 1.65. Then we can use kinetic energy. Kinetic energy can be 1/2 times 3 times velocity is 1.5 squared plus 1/2 times 2 times mass 2 is velocity 0.75 squared. 0.75 squared. Then if we calculate this by using calculator, you may use a scientific calculator. 0.5 times 3 times 1.5 squared plus 0.275 squared. 3.29375. 9375. Sure. What about Kf is 102 times 3 times 0.29 squared plus 1/2 times 2 times 1.65 squared. 0.5 times 3 times 0.9 squared plus 1.65 squared. Percent 3.9375 joule. 3.9375 joule. 3.9375 joule. That this ratio is 1. You can do so you can do by yourself. And then the next one is, in this case, what about table 4.5? Let's see this one. Table 4.5 is this we did. Table 4.5 case is inelastic collisions, and mass also different, 3 and 2 kilogram in elastic collisions. Then you have to the left is you have to choose 0% collision, then -1, 0, same. You can we're gonna do experiment. Okay. So we have to this elasticity here. Elasticity should move to 0%. 0%. Then 32 kilograms, same. Then what about initial velocity? Initial velocity is we have to see here. This is inelastic collision. Then M1 is 3 kilogram, M2 is 2 kilogram. This is elastic collision. Then we can come back to the simulator. Here is initial velocity. What about initial velocity? Initial velocity is 1 and 0. 1 and 0. 1 and 0, right? You can see here. 1 and 0. We chose maybe simple case 1 and 0. 1 and 0. Here is 1 and 0. How do we do simulate it? Initial velocity is 1. Final velocity 0. Enter. Then this is of course -1. This is 0. And already go here. Play. After collision is both the same. Is 0.6. 0.6. 0.6, yeah. There are only one because in elastic collision they stick together. It means stick together, stick together, yeah. Stick together, move together, yeah. Move together, and this is like that. Then we can find here it's a total momentum. Initial momentum is pi is equal to 3 times 1 is 3. Final momentum is Pf is equal to m1 plus m2 Vf. That is total mass is 3 plus 2 times 0.6 is equal to 3 kilogram. 3. Then momentum is conserved, right? Then Pf over Pi equal to 1. 3 over 3. What about the next one is if the initial velocity 1.5 case. 1.5 case, enter, and then go. So you can see 0.9. Final velocity is 0.9. 0.9. Then in this case, we can find the initial momentum. The 3 times 0.2 is M1 is 3 times 1.5. 1.5 is 4.5. The final momentum is 3 plus 2 times 0.9. So 4.5. Then ratio equals 1. 4.5, 1. And the next one is VI. VI is this is of course this is same 0.6, 0.9. Then kinetic energy is Ki, initial kinetic is 0.25 times m1 is mass is 3 times velocity is initial velocity is 1 squared. Then we can find this is 1.5 joule. Final moment, final kinetic energy equal to 1/2 times 3 plus 2 total mass times final velocity squared. That if we calculate this one, is 5 times 0.6 squared, that is 0.9 joule. That is, we can find 1.5 0.9 joule. This is not anymore 1 because energy, kinetic energy, not conserved for the inelastic collision. That is 0.9, 1.5. That is, we can see is about 6.6, then 0.6. 60% of energy only remained, but 40% of energy maybe emitted by the heat, heat emission, spent by wasted energy, dissipated by the heat. And then what about 0.9 K? I equal to 1/2 times 3 times. We have to remember is kinetic energy. Kinetic energy. I have to see kinetic energy. Kinetic energy. Kinetic energy. The energy. As we see, as I showed, 1/2 times mass times velocity squared. Mass times velocity squared. This is mass. This is velocity. We used this one. 3 times 1.25 squared. Then if I use a calculator to calculate this, 3.375 joule. 3.375 joule. Then what about final kinetic energy? Final kinetic energy is 1/2 times 3 plus 2 total mass times final velocity. Velocity 0.9 squared. 9 squared. And (2.20). Yeah, of course, this is less than initial kinetic energy. Then we can find Kf Ki equal to 2.025 divided by 3.375 divided by 3.375. This is 0.6, of course, 0.6. 2.025, then 0.6. Yeah, energy is only not conserved. Energy, kinetic energy, and not conserved. We can see this kind of statement. Then the next steps you can do by yourself. Yeah, this is then then what is the difference between elastic and electrical? You can write your answer there. Okay. Now I'm gonna move to the next experiment. And the next experiment is this about Hooke's law. Let me show the lab manual is Hooke's law. Objectives validate Hooke's law. Hooke's law, then analyze how different combinations of spring affect the stretching of the system. Yeah, unknown G value maybe. Hooke's law is like this. Hooke's law states that extension of a spring is proportional to applied force F equal to Kx. That's simple. If a spring obeys Hooke's law, then a graph of applied force against the extension will be a straight line whose gradient slope is K. If I draw kfx graph, then this slope can be the coefficient k, elastic coefficient k, yeah. Spring constant. You can see spring constant. Then validation of Hooke's law. You're gonna click this simulator. Then we have to click lab election, lab elect. Then what else would we need? And place 100 gram into the spring. 100 gram into the spring. Also, let me explain before starting the lab. That's lab 6. Lab 6 is Hooke's law. Hooke's law. Hooke's law. And Hooke's law is just simple. Like, you know, if we have some spring is here, spring here, then if I stretch it by applying a force F, then how much stretch the original from original length? Yeah, that's how much stretch. This is depends on the applied force, right? This F equal to kx, right? Then F proportional to the x, the how much stretch the length. This is coefficient k that is called f of x. That is spring constant. This is applied force. F is applied force. Force. X is stretched length. The extension of the string length, spring length, not spring constant, spring length. This kind of statement we're gonna check. Then also here is, as I mentioned, this one is if we draw is force and extension graph. This must be that's a linear. This is linear. Linear means the straight expressed in straight line of graph. This one. In this case, the slope is just equal to k, spring constant. Then we have to see this kind of standpoint and come back to here. So, 100 gram mass onto the spring. The spring will begin to oscillate and stop this by clicking on the mass several times or increasing the damping value to large. Yes. You have to see displacement. Click this 100 gram. Then 100 gram, we chose 100 gram. And this damping, where is it? We have to show here is a display movable line and and also damping. Damping is a lot. Then how much stretched? We can see how much stretched. Then use the ruler tool on the bottom right to measure the extension of spring with the 100 gram mass. Convert this mass to weight. Use 9.8 meter per second scale and add this data to table 1. You know, yes. How to find the weight? Weight is W is equal to mass times acceleration due to gravity. M is mass. Then in this case, we have to change into mass into kilogram. 100 gram is 0.1 kilogram. Then G acceleration due to gravity is 9.8 meter per second squared. Right. This acceleration due to gravity. Acceleration due to gravity. Then we can find this 0.21 times 9.8 equal to 0.98 Newton. And then what about extension? Extension we can find by using ruler. How much this? Okay, there's ruler. How much? It is about, you can see here. The 1.22. This is 10 millimeter, maybe 16 millimeter, 16 millimeter. 16, 17, maybe yes, 17 millimeter. 17 millimeter. 17 millimeter. Then the next one is what do we need to do? Five more result, you know, to that 5 more result, I gotta choose 150, 200, 250, 300, 340. 300 is maximum. Then I think maybe 140, 130, 100, 136, maybe another 360. I may choose another method. Maybe arbitrary method, you may choose arbitrary method, maybe 150, 200, 250, the 300, 300 is maximum. That should not, maybe 130 gram. Yeah, gram, 160 gram. Yeah, we're gonna choose only 3 values. You have to do complete all of them. But that's I want to show this because this is your work, not my work. Yeah. And then 130 grams, you can see M is 130 grams is 0.213 kilogram, and 0.213 times 9.8. That is weight can be 0.213 times 9.8 equal to 1.27 Newton, 7.4 Newton. That what about 0.16 times 9.8, 160 gram is 0.216 kilogram, 16 kilogram. It's 0.216 times 9.8 is 1.568, 1.568, 1.2568. That we're gonna check with the state. If I use 130 gram in the simulator, 130 gram, 130 gram. Message if I move to 130 gram, 130 gram, then come back to this is not the length. Oh, the here is 130 cases. How much is stretched? This you can see is almost 20, 20, 21. You can see origin rule of 22. Okay, come back to 22. 22 millimeter. 22 millimeter. If I use 160 gram, the mass should be 160 gram. In this case, we can see is 25, 26, 26, 26 millimeter, 26, 27 millimeter. We can write 27 millimeter. $27 million. $27 million. You gonna maybe you have to do all of them, but I've shown only 3 values there. Then what else do I need to do? This Newton. The other is millimeter. Then what do we need to do? The manual is shown. Then plot graph is either on paper using Excel. Actually, I prefer to show Excel. Force y-axis against the x-axis is extension. Draw a line of best bit through your point. Excel. And here you're gonna see Excel here, and then here is we have the extension as a millimeter, and then there's a force Newton weight Newton, and I'm gonna put the value what I used. That's 100. No, that is Newton value. You have to use this 0.98. You have to 0.98, and the next value is 1.274. 1.274. 1.568. 1.568. What about extension? Extension is 17, 22, 27. 17, 22, 17, 22, 27. You know, this x-axis is extension. As you mentioned, the x-axis extension, the force y-axis the force. In this case, force is weight. Weight means that this is gravitational force, gravity. Yeah, gravity is gravitational force. Yeah. And this is a force. I'm gonna draw a plot there, like this one. After choosing the range of data and insert that we have to choose scatter plot here. First scatter plot. Then we have to add a trend line. So click the data points, then right hand side to right click, then we can choose add a trend line. Then here is we have to choose. But there are lots of options there. We have to choose a linear option because this is linear. And then you have to choose option here is display equation on chart. In this way, we can see the slope of the data here. This is a graph, our graph. By using this, I'm gonna bring this data to this is the graph we draw, and then also I showed this data point to there. Then using your graph determine the spring constant of your spring is Newton per millimeter by finding the gradient. What evidence from your graph shows that the spring obeys Hooke's law, right? Because you know this in your beating. Here's almost a straight line. This, if that is not straight line, it's not that linear. That in this case, this is graph. Graph is a straight line, straight line, straight line. It means you know f proportional to the x. This is Hooke's law. Hooke's law statement is proved. And what is the slope? Slope. K equal to, and this is slope. That is a 0.0588 Newton per millimeter. Right. This is our spring constant. This is spring constant. Constant. And what else? Then part 2, we're gonna see part 2, determine unknown mass. How to get unknown mass. By using this one, you can see spring constant. Part 1, using your value spring constant in part 1, determine the mass of the 2 unknown value. You can use actually I'm gonna do some part 2. This one. Then part 2. Determine unknown masses. Determine unknown unknown masses. I'm gonna do first only blue one, then red one. You have to do yourself. Let's see here's a blue one. We can use this one. Then we have to remove blue one. I'm gonna put here how much stretched. You can find here by using the ruler. Ruler, as you saw, there is 37 millimeter. 37 millimeter. Then you can see here is x equal to 37 millimeter. As is shown here. That's blue way. Then K is we know already known as we calculate that's 0.0588 0.0588 Newton. Then by using this one, you can find the force. The force weight is equal to the force is kx by Hooke's law and 0.0 Newton per millimeter. 588 Newton per millimeter times 37 millimeter. Then this can be 0.0588 times 37 equal to about 2.1756 Newton millimeter cancel Newton. 2.1756 Newton equal to divided by, if we think 5.2, 9.8 meter per second square. In this way, we can find the mass because this is mg and g is 9.8 meter per second square. This is acceleration due to gravity. Acceleration due to gravity. Divided by 9.8. This is 0.222. 0.222 kilogram. That is SI unit. Kilogram. That this can be 222 gram. 222 gram. Oh, it says 210. And then you can find the red one yourself. Do it yourself. And then what about part 2, 3? Gravity to planet X. Okay, we have to choose gravity. We usually 9.8, but if we choose planet X, the gravity depends on some it depends on which planet. Yeah, a planet is depends on planet. If a planet is really big planet and heavy, then in that case, acceleration due to gravity higher than 9.8 meter per second squared. Then you can see here. This one. Then what we need to do by using the tool, this one is you can use of course same thing and just move back to them. If I use just 100 gram, 100 gram, then we have to use is SpaceX. This also we use the SpaceX, planet X. We don't know acceleration to gravity there, but we can hang 100 gram there. That this O is and is like this. How much? 20, maybe 24 millimeter. We have to use the M equal to 100 gram case. That's extension is 24 millimeter. 24 millimeter means, W is equal to F is equal to K times X. K, we can use the same K, 0.2058, 0.2058, 0.2058 Newton per millimeter times 24 millimeter. Then 0.2058 times 24 millimeter. That is 1.112 Newton. Yeah. Then we have to see here is M, W equal to M. In this case, not just G, just GX planet. We need to find the GX planet. What is a GX planet? Then GX planet is equal to weight divided by mass. Mass, as I said, 100 gram. 100 gram is M equal to 100 gram is 0.1 kilogram. 1 kilogram. And 0.1. That this is 1.112 Newton kilogram. And this can be 14.112 kilogram meter per second squared. I think this planet is bigger than the Earth. So our Gx equal to 14.112 kilogram meter per second squared. The next one is point 4. Analyzing systems of strings. That in this case, we have to choose the second systems, Hooke's laws, and the second systems. Then we have the two kind of cases, two springs. What happened? You can do it yourself. This is by using. I have to choose this second one. Then I guess you can do it yourself. That's all. Okay. Have a good day.